Okay, so I think we can start. Can you hear me well? Okay, so let's start. Welcome everybody. Today I will do the lab session, and we are in week 5, and we will do as follow. First, we will go through this walkthrough on logistic regression, so what you just saw during the class, and then we will do a few exercises. This one. Okay. So open in Colab. So they are on the GitHub. You can also follow on your own computer. Okay, so the topic of today was classification, which is a part of supervised learning. And the objective is to correctly assign objects to different categories or labels. For instance, to classify emails as spam or not spam. Okay, the table of contents of this walkthrough is written here. So we will start with a summary of some important concepts. Then I will go through a basic example. So I will create a data frame from scratch and explain some of the concepts seen during the class. Then we will go through a real example where we will try to predict advertisement click. So a real life example. And then at the end, we will go through multi-class regression. So we will try to, multi-class, this means that we have more than 2. This is not in binary, because the first 2 are binary classification problems, and we will then do a multi-class regression problem. Okay. So some important concepts. We will use the following example. So we suppose that we have a sample of 100 people, and 20 among them have purchased a certain product, 20%. And we want to predict whether a person will buy, binary 1, or not buy, binary 0, the product based on her characteristics. For instance, whether this person is a male or female, her age, and so on and so forth. So the first and important concept is the base rates. What is the base rates? The base rates represent the degree of accuracy you would obtain without using an algorithm. So this is also called the prior probability of the most common class. In the example I just mentioned, we have the probability in our sample of buy is 20%, and the probability of not buy is 80%. So this means that you would obtain an accuracy of 80% without using any algorithm if you classify each person as not buy. So the aim of our approach is to outperform these rates. Otherwise, this doesn't make any sense. Okay, and when talking about accuracy, as you also saw during the class, accuracy is defined as the number of correct decisions for a model, for methods, divided by the total number of decisions. So in our case, if we do classify 90 people in the right categories, we will have a an accuracy of 90%. And obviously, and as mentioned previously, this should be greater than the base rates. And lastly, I also want to review the true positive, true negative, false positive, and false negative. So first of all, the true positives. A true positive is when the algorithm classifies the instance as positive. So in our case, by, and the true label is also positive. So we are fine. A true negative is also fine because the true label is negative. So in our example, not by, and the algorithm classifies it as negative. So we are also fine. And problems comes when we have false and also two. False positive means that the algorithm classify the instance as positive in our example by, but the true label is negative. So we made a mistake. And the other way around is also possible. False negative, the algorithm classify the instance as negative, not by, but the true label indeed is positive. So, and you saw during the class that we can summarize those concepts using the so-called confusion matrix. Okay. Is there any questions so far on those concepts? I let you 10 seconds. Clear so far? Okay. Okay, so let's start then with the code. So we, first of all, like always, we import the required packages. So as always, NumPy, Pandas, Seaborn, and Matplotlib for the plots. And we will need the label encoder and one autoencoder to encode the categorical variables. We also need the standard scalar to standardize the features. We will see this. Of course, to train our model, we will use the logistic regression. Before this, we will have to train to split our sample between test and training sets. We will use the iris dataset from sklearn in the third part of the lab. And of course, confusion matrix and accuracy score, precision score, recurse score to assess the accuracy and performance of the logistic regression, and also unique levels. Okay. So the basic example. So I created a data frame from scratch. We have a categorical variable, the group A, B, C, or D for each instance. We also have, I can run this. We also have two numerical variables, x1 and x2, which are between 0 and 1. And a binary variable, the target, is what we want to predict in this example. So first of all, we want to show how we can encode the categorical variable, the group. So we will use one-hot and label encoding. So one-hot encoding creates a dummy variable for each category. So like this. in the example, we see, for instance, that we have A, B, D, and so we have A, B, D. So it makes dummy variables according to the different categories. So it adds, basically it adds a new column for each category. So we can go from, this way we can go from categorical variable to a numerical one that we can use in our model. This is the aim of encoding, to be able to use a categorical variable in the model. So we have to transform it into a numerical variable. So this was the first way. And label encoding, we assign integers to the different categories. And this is useful for ordered data. For instance, if it would be a grade, the group would be a grade. A is the best and D is the worst. This should be useful because it's we can how do you say it in English? We can it reflects the different spaces, or for instance, between A, which is A, I can also do this. Between A and B there is 1 unit, and between A and C there is 2 units. So it represents the space. This is not the best word for it, but this represents the space between the different l'écart in French, between the different the interval. Thank you, the chat. The interval between the different categories. So for ordered data, this is useful to use label encoding, and also for data that is not ordered, like this, like in our example for the group, we would prefer to use one-hot because it doesn't have because otherwise maybe the algorithm will believe that there is an order, but this is not the case when there is not. Okay, so this is about encoding. Okay, any question on encoding? 10 seconds. Okay, fine. So we are now interested to plot x1 and x2 according to targets. So we generate a plot using the plot.plot.scatter methods from Panda, and we don't see it well, but the target is 0 or 1. 1 is blue and 0 is red, and we see a clear separation. Points with the low value of both x1 and x2 seems to be in the first class with target equals 0, and points with a high value of x1 and x2 are in the second class here above with target equals to 1. And we can compute the base rates of this simple exercise, which is the probability of the most common class. In this case, we have 10 instances, 5 and 5. So if you would classify randomly, not randomly, if you would classify to one class or the other, all instances, we would have a success rates of 50%, because there are 5 out of 10 in both classes. So we have the maximum of the first class, the length of the first class divided by the length of the entire data frame, and the length of the second class divided by the length of the entire data frame. In this case, both are 50%, but this may be different. Okay, so 50%. This we will have to outperform this rates in using our method. And the aim of classification is to find the best fitting line. We can see on the graph something right here could be fine, maybe here, I don't know, to find the best separating line between the data. This is the aim of classification. So let's do this, and we use there are many algorithms, and in our example we use logistic regression, and this line is called the decision boundary. Okay, so this code basically fits a logistic regression. So we select our variables and targets. We create an instance of the class logistic regression, and we fit the model on the selected variables. And then we want to plot also the decision boundary. So we create a lot of points using this code, and we plot them. So we predict for those points here. We predict the value, and then we plot all points using the matplotlib, and this we will see then the decision line, because if we generate points on the wall graph, we will then see the decision boundary. Also, we will plot the training points, those ones with the right colors, and also 2 points, 0.4, 0.4, and 0.5, 0.5, for which we want to predict. We will see it later. So what does it give us? So we have the decision boundary, so the points, the 5 points of the first class, the 5 points of the second class, and our 2 points. And this is then the decision boundary. So with all those points that we generated and computed the prediction and then plots, this makes the decision boundary. And we are now interested to check if it works. So for instance, for P1, which is right below the decision boundary, this should forecast the class 0, and for P2, this should forecast the class 1. And we can create a data frame with those points and use the same class, the same instance of the class, the method predicts with these points to check whether it works or not. And obviously it works. So it predicts for the first point, 0.4 and 0.4, it predicts the class 0. And for the second point, P2, it predicts the class 1. So it worked. And of course, we are also interested to see if we do better than the base rate. In this case, what is the score of the model? This is quite easy. Maybe someone can speak up or write in the chat. Nobody? The score of the model, this is the accuracy. This means in our training data, how many, this is the number of right decision divided by the total number of decision. So we have, as Miles says, there is no mistakes because this is a basic example that I generated myself. So we have an accuracy of 1. We did no mistake in the training set. So the accuracy is 1. We correctly classified every point in the training set. Okay. Is there any questions on the basic example? Something that is not clear? 10 seconds. Okay, fine. So the second topic of today is to predict the advertising click using, again, logistic regression. We have the link to the data set on Kaggle here, and we first load and explore the data. So, okay, so we see that we have 10 rows, 10 instances, and 10,000 rows and 10 features. Sorry. So for each user, we have the daily time spent on site, which is the user time on site in minutes. We have the age of the customer, not customer. We have the area income, which is the average income of the geographical area of the user. We have the daily internet usage, the average minutes a day consumer is on the internet. We have the headline of the advertisement. We also have the city, whether the person is a male or a female, the country, a timestamp, and the target variable, what we want to predict, is whether or not the user clicked on the advertisements. Okay, so we want to use those features, those 9 features. We won't use some, but we want to use those features to predict whether or not a user clicked on the advertisements. So let's print some information about our data. So we can see that we have no null values. In addition, we can also see that the timestamp should be a datetime, and this is an object. We will modify this, and all other variables are fine. So daily time spent is a float, age is an integer. Everything is fine except timestamp. So we change it using the two datetime methods, and we then see that it's all fine. Okay, we can describe, so generate a bit of statistics from those data. So for instance, we have that the age repartition is from 19 to 61 with a mean of 36 and so on and so forth. We also see that there are half of the users that clicked on the ad and half who did not click because we have 0.5. We also see that there is a bit more women than men, 0.48, and so on and so forth. So a bit of statistics. But what is more interesting is to To plot those statistics, for instance, the age repartition, we can plot the age repartition. We can see that the majority of people are between, let's say, 25 and 40. Okay, time on site, we can also plot it. We can see that there is a peak at between 75 and 85 minutes on daily time spent on site, which is quite big, quite long. And more interesting, we can also do joint plots. For instance, between the daily time spent on site, we don't see it well, and the age, and we see, for instance, that there is more points here. It means that younger people spend more time on site on average, but this is not true for everybody. But there is on average a bit more points here. We can see this, and we can do the same with the daily time spent on site and the daily internet usage. And we see that there are two clusters, or yeah, maybe two clusters, people on this part of the graph who spends less time on the internet and also less time on site, which is then which makes sense, and also people who spend on average more time on internet. They also spend more time on the sites. Okay, and again, more interesting is to see this colored using the target variable, so the clicked on ad, for instance, here. So this pair plot from Seaborn is very useful. It's just one line, and you have everything then plotted, and you can already get a good insights about your data. So, for instance, okay, we will take. I have here just one example to illustrate this. For instance, this is the same. So the average we have on this axis the daily internet usage and the time spent on site, and we can see that people who spend more time on both internet on average and on the website don't click on average, or on average have a lot more chance not to click on the ad. And on the other side, people who have a lower internet usage and a lower time on site are more likely to click on the ad. And we also see this here. People who spend less time on average daily on the internet have more chance to click on the ad than people who spend more time. Okay. So everything's clear. Does anyone have a question? Okay. Fine. Can someone write yes in the chat so that there is a bit of interaction? Yeah. Okay, no questions. Thank you. So okay, this is fine. We have already some insights, some information about this data. We can already imagine that there is a way to forecast, but we have to fit a model on it, and that's what we will do now. So we will fit the logistic regression. I will let you read this first part theory at home. So you're at home, but on your own. This is a recap on linear regression, on logistic regression. So the equation, and yes, I will let you read this on your own. And we start with the code. So of course we will need to know the base rates. And in this case, we saw before that there are 500 people. So these are the people who did not click on ads, so null, which have a 0 here. And there are 500 people who did not click, and 1,000 in total. So this makes a base rate of 50%. If we have the max of this is the same formula as before in the basic example. We have 50%, because 50% of people clicked and 50% of people did not click on the advertisement, and this makes 50%. If we classify everybody as click or not click, we will have a 50% accuracy. So let's again see the data, and we see that some variables are categorical, so we will have to encode them, the city, for instance, and the country. So we use, in this case, label encoding using these cats.cat.codes methods, because it would be not so nice to have, because there are like 200 countries, this would be not so nice to use one hot encoding, because this would add like 200 columns to our data frame, and we don't want it. And cities there are like 800, 900 cities, so we use label encoding for this. Let's run this, and we see, for instance, that okay, every city has been replaced by a numerical value, and every country, the same for every country. Okay, and we use now, we have to select the variables we want to use. So we will drop the add topic line, because we do not know yet how to do with this text. We will see next week how to do it in text. And we also drop the timestamp, because we also don't know how to do with this. And of course, we drop the clicked on add, because this is the target variable. If you would not drop it, we would have an accuracy of 100%, because this would be a linear model. Okay, why is the of course what we want to predict? So clicked on add, and if we see this, so we will use those variables. They're all numerical, so this is fine to predict this. There is one thing, integer. To know the type of a column, do you just do data? Yes, to know the type, I could do, for instance, so there is a question, more question. Okay. If I do this now, we will see. So the question is, to know the type of a column, do you just do data.dtype? Yeah, this is true. You can do this with a S. And if I run this now, we will see that this is integer. But before this was objects, you're right. This is not category, but we do everything in one line. Here we transform it. We transform the data into a category, and then we use this method to encode it, and then it's then numerical. Does it answer your question? Okay, I didn't get why we dropped the 3 columns. So we are there. Okay, on we drop. So I think clicked on add is fine, because we don't want to have the target variable in our predictor variables. This would make no sense. And those two, since we need numerical variables, they are not numerical. We don't know yet how to do with text, so we cannot use it. This is the topic of next week, how to manage text variables. And the timestamp, we also don't know how to do with this, because we need, in order for the model to work, we need to transform every non-numerical variables into numerical variable. And we will see how to do this with text next week. And timestamp, we could do this, but using, for instance, 1, 2, 3 according to the, or maybe the day and the month, but this is not useful in this case. Does it answer your question? Great, thank you. Okay, fine. Okay, so the next step is to split the data in 2 sets. We will use the first one to train the model, so to learn the right parameters, the optimal parameters of the model. And the second one, we will use it to test the model. So we will forecast based on the test set and compare our forecasts and the true values. Why do we do this? Because it could be that we do overfitting, and with overfitting, if we do if we run the model on the 10 instances, on the 1,000 instances, it is probable that there is the possibility that we overfit the model, and we won't notice this. So we do this split to avoid or to check if we overfit or not. So in this case, we use the train test split function from sklearn with a test size of 20%. So in this case, this is 200, 1,200. And I set the random state at 42, so that the results, so that it always do the same random splits, so that we can then compare and reproduce the results. So what does it give us? This gives us a training set of 800 instances and a test set of 200. So 80%, 20%. We can also do 30% in general. 25 is also fine. So it depends on your problem in general. Okay. So let's fit the model. So we first create an instance of the class Logistic Regression. Then we fit on the training set. And we predict for the test sets. So Y pred is the prediction that we will compare to Y tests, to the test data. So this gives us like the prediction is 1 or 2, clicked or not on, clicked or didn't click on add. And the true values are those ones, those 200 that we have now to compare to see the accuracy of the model. So for instance, the first one is a mistake because the model predicts not click, and the true value is that this person clicked on the ad. The second one is fine. The model predict click and the true value is click. Okay. Any questions so far on this train test splits? Okay, no question. I wait 10 seconds more. Okay, that's fine. Okay, so we want to evaluate the model. How good do we predict? So I have a function evaluate where we compare the true and the prediction, the true values and the prediction. It computes the precision. I don't know if you saw this in class, the recall and the F1 score, and also the confusion matrix, the accuracy score, and that's it. So if we run this, so we have y test and y pred. We want to come to check, and this gives us the confusion matrix, the accuracy score, 89%. We are fine because we are satisfied because we outperformed the base rate, which was 50%. So we did much better than the base rates, and there is also a precision of 95. Recall, I will explain this later. There is one thing. Okay, we can. This is written without the precision recall in F1. Okay, so concerning the true negative, false positive, false negative, true positive, we can also do something like this because we have to be careful. We don't know which one is what. Oh, sorry. Which one is what? So we may be confused. So we can use this to see which one are the true positive, the true negative, the false positive, and the false negative. And in this case, 93 are the true positives. It means that we, out of the 200 in the test set, we classify 93 as positive, and they were indeed positive. This means that you classify them as clicked on ad, and they clicked on the ad. The true negatives are people that the algorithm classified as negative, not click, and they were indeed they didn't click on the ad. False positive, the algorithm classify 4 people as clicked on the ad, but they did not click in for real. And false negative are people who clicked on the ad and were classified as did not click on the ad. So we can see that the accuracy, so the accuracy is 89. This is calculated as the correct decisions, 85 plus 93, which is 178 over 200. This makes an accuracy of 89%. The precision is defined as among the positive cases. So among what the algorithm says it is positive, how many are really positives, are in reality positive. So the true positive divided by the true positive and the false positives. This makes almost 96%. So if a person is if a person is classified as positive, as clicked on the ad, there is a 96% chance that this is the case in reality. The recall is something else. Is defined as true positives divided by true positive and false negatives. And in this case, this is 93 divided by 93 plus 18, which is 83, 84 almost. And okay. And the F1 score is not so important. This is sort of an average between the precision and recall, because we have to know that if we increase the precision, we decrease the recall, and the other way around is also true. If we want to increase the recall, we may make, for instance, if we increase the precision, we will want to limit the false positive, and this will increase the false negative, or something like this. So the F1 score is the mean between precision and recall, a sort of mean, the harmonic mean, in fact. Okay, so any questions so far? Okay, so there is one. No, thank you, George. Maybe George wants to go quickly. Okay, fine. Okay, what we can do is to do the same, but before doing the split between train and test sets, we can standardize the data. So as it is written, standardization is helpful to give the same weights or importance to each predictor variable. So the aim of standardization is to resize this is the S, what is this? To resize the features so that their mean equal 0 and their standard deviation equal 1, so that they all have the same importance, because if a variable is way bigger than another, this will have a greater importance in the prediction, and we want to avoid this. And sometimes this is a very powerful, we will also see this is a very powerful methods to make the algorithm way better than before. So we standardize the features using this class standard scalar, and this is important. We have to standardize on the training sets because otherwise this is cheating, because we would use information of the test sets in the standardization, and we want to avoid it. We transform both X train and X tests, and then I created a data frame to show you how it looks like. So these are the standardized values. So so with a mean of 0 and standard deviation of 1. If I do describe, we can see that the mean is 0, minus 17, minus 16, and so on and so forth. The mean is 0, and the standard deviation is 1, approximately. So so yeah, 1. Okay. So, and again, we do this in order to give the same importance in the prediction to all variables. Okay, and then we do the same. So we create an instance of the logistic regression class. We fit the model. on the training data, and we predict on the test data to have our prediction, and then we evaluate the prediction by comparing the true value y test and our prediction y prediction standardized. And we see that we made we have a better we have better result, we have a better performance using standardization. If we see here, for instance, the accuracy score is 96 now, which is really, really good. And before it was like 80, 89. So we increased almost, I think we increased everything. So 89 is increased, 95, 83. And here we are 97, 95. So everything has been increased. The performance, the accuracy, the precision, the recall, everything has been increased using this standardization. So think of it, for instance, in the project also, this is a good way to increase the accuracy of your model. So, and of course, the rest is, everything is the same. So this is the same splits. This is the same. So only the standardization makes the difference. Okay. So only 8 mistakes out of 200 instances is fine on the test set. So this is fine. Any questions so far on this standardization on, for instance? Okay, fine. Is it clear so far? Does everyone understand what I say? What I try to explain? They all sleep. Okay, we need some review, but okay, yeah, maybe this is too quick, but we don't have as much time as, yeah, you have the notebook in every case. I try to do it as complete as possible. Yeah, but I don't really understand why it increase all the data. The 3. I don't understand your question. Okay, standardization is a way, as I said, it gives the same importance to all the features, and in this case, this means that on the previous example, we had like no standardization, and maybe some features that didn't have a good predictive power had more importance, and we reduces the importance of those features in order to give the same weight to all, and maybe some features that were a bit not so important in the because of the size, just because of the size. It depends on the size. If I go back to the data frame, just for instance, the area income. I just check the chat. Like an homogeneous ponderation. I don't know what you mean with this, but if you see here, for instance, the area income, which I don't think is maybe it is a good predictor, but it has in every cases just because in absolute value this value is greater, this takes a greater importance in the prediction than the other ones. And by standardizing, we avoid this. We make all features have the same weight in the prediction. And that's why maybe the daily internet usage, as we saw earlier, this is more than useful to predict the ad click, and this would have been not so. Yeah, this is difficult to explain, but yeah, just because of this value is greater than those one in absolute value. All values here are greater than those ones. This takes a greater part in the prediction. I don't know how to explain this. And by standardizing, we just reduce and put all the features we give all the features in the same weight, so that the algorithm can better recognize which feature is important and useful for the predictions. And this makes in general the prediction better, as we see in this example. I hope this answered your question. Okay, I think I understand. Thank you. Okay, so that's it with the second topic, and now we are interested in the multi-class regression. So we have more than 2 target classes. This is not only click or not click. This is there is 3 target classes. We use the well-known iris data sets. Don't know if you know this data. And it looks like this. So this is our features. These are like length or something, or width of flowers, and we use this to classify flowers into 3 categories. So 3 classes. The 3 classes, so 0, 1, and 2. By the way, we have, I think, 150 data points. And as always, we do the same. So we split the sample into training and test sets. We fit the model on the training set. We can compute the accuracy of the training sets using the score X train, Y train, and this gives us an accuracy of 81%, which is not so bad. And we can also compute the accuracy on the test set, which is 87 almost %, which is bigger than 81 of training set. This is not usually the case. Normally this should be a bit lower, but in this case this is greater. And I also have here, so the true values. So actually I have a data frame below that summarizes everything. So let's do this here. So for each, so this is the train, the test sets. This is our test sets, and we have because actually the algorithm assign probabilities for each class to each instances of the test sets. So for instance, there is the first instance here. We predict 2 because there is a 51% chance, according to the logistic regression, there is a 51% chance that it belongs to this category, while the true class is 1. So we made a mistake, but this is not so obvious here, between 47 and 51%. The second one, for instance, predicts 1. and the true value is 1, so we are fine. And for instance, the fourth one, I have a probability of 99% that for 0, and we don't make mistakes in this case. So this is also interesting to see the different probabilities of each class. And of course, the model takes the class, predicts the class with the highest probabilities. Okay, so we use the predict proba method of the instance of the class, and also predict, of course. So any question, and this is the same. True value, prediction, and probabilities. Okay, any question on that? So the only thing to remember is that the logistic regression algorithm assigns like every classification algorithm, they assign probabilities to the different classes and predicts. The prediction is the class with the highest probability. Okay. Any question on this? Okay, fine. Okay, is it clear so far? Should I re-explain something? Okay. George is very active. Thank you, George, for your participation. Okay, so we can further go with the confusion matrix. We will see that this is 3 by 3 because we have 3 classes, and we see that we the algorithm classifies everything correctly except for instances that are incorrectly classified. That's why the accuracy was high. We have only 4 errors out of 30 data points, which is not so bad. There is something in the chat. So the question is, you're talking about multi-regression or still talking about logistic regression? Actually, this is 2 different concepts. Multi-regression means that this is basically the same. We use logistic regression in both cases, but multi-regression means that we have 3 or more classes, in this case 3, and logistic regression is only one algorithm to do multi-regression or binary regression or binary classification. Maybe the title of this maybe the title of this topic is not so clear, but multi-regression means classification using logistic regression for more than three or more classes, and logistic regression is just the algorithm to do multi-classification, multi-class regression, or whatever you want to call it. Is it clear? Okay. So here we have a function to plot the confusion matrix. You can look at it on your own later. Basically, it plots the confusion matrix in a more beautiful way than only this array. And if I run this, on the test set, the confusing matrix for the test set. So it shows basically the same, that we only did 4 mistakes and that we correctly classified the 26 other ones among the 3 different types of flowers. And we can also do the same as before with the decision boundaries. So we generate a lot of points, and we predict for them, and we also then can define the decision boundaries. In this case, there will be 3. There are 3 classes, so the decision boundary will be a bit different. And we see if I run this, that we have all 3 classes. This is on the training set, on the test set, sorry, and it correctly classifies a lot of points. And we have our 4 mistakes here. So basically, this is another way to represent this. And also, we have the decision boundaries of the model with the 4 points that are incorrectly classified, which corresponds to the 4 points here in the. So we see that it predicts this type, and basically this is this type for 4 points, and we have the class. So I think it's clear. And lastly, finally, we can do the same with the training set. So basically, I will go quickly on this because this is the same, but for the training sets. So there are just more points. So confusion matrix, we see that there are 22 points that are incorrectly classified. The rest is fine. And also the decision boundaries on the training set. We see the points that are. So we see the points that are incorrectly classified in both those classes. Okay. So we are done with the walkthrough. I think this is 1.5 hours. So maybe we take some time to go a bit through the exercise now. We can do this. So any question on this walkthrough? General question about classification, logistic regression? Okay. So we can do the exercise. So we use in this exercise the Titanic data that you also saw during the class. There is this this exercise is on the GitHub. The solution is not yet posted because I want to make it a bit interactive. We can try to solve it together. And basically, so we use, I import everything for you, and basically, so we use the Titanic data. So we have, I don't know how many, but a lot of instance, 80,000 people for which we have the class 1, 2, or 3, first, second, and third, the age, the sex, and the survival status, or survived or died. I make a bit of data cleaning. You can follow with me on your own computer, of course. So a bit of data cleaning. We see that we have, for age, we have some missing values here. So we drop them. We drop all missing values and we end up with thousands instances of those data. Okay. And in the following, I ask to answer the questions. We already have the results. So for instance, here you already have the result of the one-hot encoding, and you have to write the code. So write the code where it's written your code here. You already have the result. You can obviously also add code so that you can try without destroying the results. And we can go with this exercise until like 5, and then we will see how far we come. So you have to only to okay, I think you understand. So well, there is your code here. You can simply write your code, or the three dots. You can only, it means that you also have to write something. And I will let you like 3 minutes. Basically, this is all. This is, if you have the other notebook, you just have to copy and paste, and you have the you have the solution. But try to think about it. Okay. So any question on what is to do? I will let you like 3 minutes per question, and if someone then wants to show his solution, then he can take on, or I will show the solution. Is it clear? Okay. So 3 minutes until 45, and then I go with the first question. If you already got it, you can write something in the chat so that you have it. Okay, does anyone has a solution for the first question, or for the at least the one hot? Okay, David N. This is the right answer in the chat. Yeah, so we'll go through this one, but this is correct, David. So we first create an instance of the one hot encoder class. Then we want to transform using your or a predefined or class or instance of the class. Sorry. So we fit and transform the data we want to transform, to fit and transform. So this is the class. And we use also this toArray method to make it an array. And then we can do this like we can do it like this, but this gives us an array. I can show you, for instance. So this gives us an array. What is? Okay, I did something wrong, maybe. What did here is wrong because I need to take this. Okay, this makes an array like this, and in order to show this a bit better, we can do a data frame with it. So I just take the correction from the chat, which is right. If I can take it. So basically this doesn't work. So I have it also here. Okay, so basically we make a data frame from this array where we with the column of the categories of the one hot, and we end up with this. So that's right. Does anyone has an answer for the second one? The label encoding. This seems to be, so Hannah suggested an answer. This seems to be correct. So like before, we first create an instance of the class, then we okay, yeah, we can do. Yeah, this is right. Then we transform the data and using this label encoder. So that's quite easy because we have those packages. Without it would be a mess. So we use the fit transform method, and on the variable we want to transform, and then we are done, basically. I hope yeah, okay. So that's a solution. Yeah, that's fine. We also could do this in one line. I show you like this, just chat. Okay. Like this. So on one line where we make the series of the label fit transform the data, and we also add a name, and this gives us the same results. So the third one is basically the same, so I will skip this and already write. This is basically the same, but we replace the variable, so we can run this. And finally, we can concatenate, all the data frame into one. So we concate the initial data. We have the cat to one hot that we have to concate. We also have the label encoding of sex. This is, you have to write your own variables, right? And the label encoding of survival. Axis equals 1 means that we do it on the columns and not on the rows. And this should work. Okay, this works. So we have our original data frame, and we added the data according to the labels. So one hot according to the encoding. One hot encoding for this one. For the sex, female is 0, male is 1, and for the survival status, 1 is survived, 0 is died. So we will use, and the age is fine because it's already numerical, so we don't have to transform this. Okay. Any questions so far? Okay. So for we will do the second part, and I will leave you the third part because the third part is almost the same as the second one. So we will do the second part, logistic regression part 1, and then we will be done. So yeah, 7 minutes maybe, and then we do it quickly. So at 5 we do the correction of the second part, and then we are done. Okay. And if you already finished, then it means that you are not so bad. Okay. So at 5 we will correct this part 1 of logistic regression. And of course, if you have any question, feel free to ask now, so that we have 5 minutes before the correction. Okay. So does anyone figured out to do this question 2.1? What is the base rate in this case? Or do you need more time? I don't know. So nobody. Do you hear me? Why can't I forget? So nobody for question 2.1. What is the base rate in this case? Okay. This seems to be correct. So yeah, this is correct. So we want to, if you go to the chat, we want to have the maximum of the maximum probability of the most common class. So in this case, this is correct. So I will copy and paste your answer. If I can select it, but it won't work, I think. Let's try again. No, it doesn't work like this. So I will just do it on my own. But this is correct, yes. So we want a maximum of the length of the first class. So 0. For instance, if I do this, this gives me the length of the first class. So for the people who died, if there is no mistake, there's an invalid syntax. I need to. So 619, this is the length of the first class. The length of the second class is lower, so it means we have to use this one, but with the maximum it was fine. And if I divide by the length of the whole data frame, this gives us the base rate which is approximately 60%. Okay, so 2.2. Does anyone have an answer for this one? The maximum, Brian, is because we want the probability of the most common class, because it would be intelligent to classify. If you don't use any algorithm or any approach, you would classify every instance as the value in the class of the most common class. So if we take this example, I would classify without any algorithm, everybody has died, because I would have a better accuracy because more people died than survived in this case. So this is the probability of the most common class. Exactly, this is the maximum of the probability of the class 0 and the probability of class 1. Okay, nobody for 2.2? Okay. Okay, fine. So this is actually basically easy. We only have to take the age and the sex code off because we want the encoded variable, and y is what we want to predict. There is a mistake here. So what we want to predict. So the survival status code. And if I print X, we have the data. So we want the age and sex to predict the Y, which is the survival status, but always the code, of course, so the encoded. Then I train test splits the sample. I divide like before between training data and test data. Then we create an instance of the class, of the regression class, and what should be written here in order to fit the model? Does anyone has the answer to this one? This is actually basically easy. Anyone? Nobody? Yes, that's right, Diana. We want to fit the model on the training set. So we use X train that we defined before, and also Y train. This is the predictor variables. So if I do this, if I do it like this, these are our predictor variables of the training set. So we have only 836 because we only have a part of the whole sample, and the training target is Y train, which is like the survival status code of the same length, so the corresponding one. So we fit the model on the training set. So we use the training set. We fit the model, and then the train accuracy, how to compute it. Basically, we need to use the training data. So this is the accuracy, how many, what is the percentage of correct decisions in the training set. So this is like George says the same input. So that's right, X train and Y train, which gives us an accuracy of 80%, 79, which is better than the 60% of the base rate. So we are fine. The model works better than the naive method, which would be to assign to the most common class. The test accuracy is basically the accuracy of the test sets. So in the test sets, how many, what is the percentage of correct decisions in the test sets? The inputs are basically the same, but for the test sets. So X tests and Y tests. This gives us an accuracy of 72%. We are also fine because this is greater than the base rates. And how to compute the prediction? What should I write here? Somebody should write it in the chat. This is not so complicated. To compute the prediction, we have to so we use the instance of the class with the predict method, and we compute it on the test set. So we predict for X test. This gives us the prediction that we compare then with the true values, Y tests. And this gives us then our confusion matrix and accuracy score. The accuracy score is the same because we already computed it here. And we can see that the precision is not so good in this case. Accuracy and precision is not so good. We can also see this in the confusion matrix. There are a lot of mistakes, but this is also because we only use two predictor variables in this case. Question 3 is basically the same with all variables, and we see that the score increases, the accuracy increases. Actually, I can show this. The accuracy increases too. Well, not so much, but a bit. Okay. So I think this is enough for today. We also would predict for a man aged 50. I can do this quickly. So for instance, for men age 50, we define the person according to its characteristics. So it's a man which is 50, and it's a man, so it's 1. And we predict for this man, and this gives us that this person dies. And if we do the same with the probabilities, we can see that so we predict the probabilities of man. We can see that the probability of the first class, so die, is 76%, and the probability of the second class is 23. And basically the rest of the exercise should be possible now, because this is basically the same with all the variables, so it should be easy for you now. Okay, so thank you for being here. I will post the solution. I will post the solution, also post the solution on the GitHub of the exercise. Okay, so thank you for participating to the lab. I hope this was my first time, so I hope it was fine. I will try to improve myself for the next time maybe. Yes, thank you, and see you soon. Good luck for assignment 1, and yes, see you soon. Thank you. Or maybe there is a question. I can answer a question, but the session is done yet. No. Okay. Maybe Diana is here. I can answer this question. Yes. Does it matter to what you set the random state? No, you can specify any number you want. This is only useful to reproduce the results so that it always do the same splits. So you can set any integer. I don't know, maybe yeah. You can set any random any integer, the integer you want, and it will split the data. (2.3) Is David here? No. Okay. Oh yes. Can you please scroll to 2.3? Is there 2.3? What is the previous? Well, okay, this one. Oh, sorry. This one. Why does it? Okay. So I will post the solution on the GitHub.